Ever trying to train like a super smart AI, you'd think just, showering it with data would be the best way to teach it, kind of like cramming before a big test. But as it turns out, it's not that simple.
Yeah, it really is fascinating. It's almost like giving someone a cookbook and expecting them to become a master chef overnight.
Hmm.
In AI, these direct methods where you just feed the model all the data at once sometimes fall short.
Oh, right.
Right.
It's almost counterintuitive. Our deep dive today explores this interesting paradox. We've got this research paper, All Roads Lead to Likelihood, Value of Reinforcement Learning and Fine-Tuning, and it dives right into why these indirect approaches, using things like reinforcement learning and reward models, can be surprisingly effective.
Yeah, and the paper really sets out to answer this question. What's the advantage of using a more complex two-stage process involving a separate reward model and reinforcement learning if the ultimate goal is just for the AI to learn from the data?
Okay, so before we get too deep, let's make sure we're all on the same page. What exactly is fine-tuning when we're talking about these large language models?
So think of fine-tuning as taking a brilliant student who already has a vast general knowledge base and then honing their skills for a specific task. We start with a pre-trained model and then refine it for something specific like summarizing complex texts.
So it's like taking an AI that knows a little about everything and turning it into a specialist, like an expert in, say, writing marketing copy or translating languages.
Exactly. And there are different ways to do this fine-tuning. One way is called supervised fine-tuning, where you provide the model with labeled examples, almost like giving it a textbook with all the answers highlighted.
Makes sense. So what's the other way?
The other way is called preference fine-tuning. In this case, you train the AI based on comparisons, showing it two different outputs and indicating which one is better. It's more like a tutor giving feedback on different approaches to a problem.
Ah, I see. So one method is very direct, here are the right answers, and the other is more about guiding the AI to figure out what works best.
That's a great way to put it. And within preference fine-tuning, a particularly popular technique is RLHF reinforcement, learning from human feedback. Here is humans who provide the preferences, essentially acting as the tutor or judge.
Okay, so we've got these different fine-tuning methods, but here's what I don't get. If we just want the model to learn from data, why not just use maximum likelihood estimation? Just give it the data directly and let it figure things out.
Well, maximum likelihood estimation, or MLE, is a way of training a model to make predictions that are most likely to match the data it's given. You're essentially asking the model to learn the data's underlying patterns and reproduce them. It's very intuitive, which is why it seems like the obvious approach.
So it's like showing the model a bunch of cat pictures and saying, figure out what makes a cat a cat.
Precisely. But the paper challenges this assumption that MLE is always the best way to go. It's highlighting the paradox. Why bother with this more roundabout two-stage process with a reward model and reinforcement learning?
Right. If the goal is for the AI to learn from the data, why wouldn't we just give it the data directly? What's the advantage of this indirect approach?
That's the million-dollar question. And to answer it, the authors had to do some serious myth-busting. They looked at a bunch of popular hypotheses about why RLHF and other indirect methods often outperform direct MLE.
So they're playing AI mythbusters. I'm intrigued. What were some of these myths?
Well, one common belief was that on-policy samples are inherently better. This means using data that was generated by the model itself as part of the training process. It seems intuitive feedback on your own work should help you improve.
Right, like practicing a speech and then listening back to the recording to see where you can improve. So did they bust this myth?
They did. The authors found that while on-policy samples are helpful, they weren't the main reason for the success of these indirect approaches.
Interesting. So what else did they look at?
Another hypothesis was that offline methods, the ones that rely on data collected independently from the model's own actions, struggle because they have difficulty staying close to the initial pre-trained model. But again, their findings didn't fully support this idea, and they even tested whether the choice of optimizer, which is the algorithm that helps the model learn from the data, played a role. It turns out it wasn't a major factor either.
Okay, so it's not just about the type of data or the technical tools used for training. This is getting more and more curious. What about the data used to train the reward model? Maybe that's the secret sauce.
That was another idea they explored. Maybe reward models, which learn to evaluate the quality of different outputs, simply perform better because they can be trained on more diverse data sets.
So maybe it's a case of more data, better performance.
That's what they thought. But even when they restricted the amount of data used for training the reward models, the indirect methods, often using RLHF, continue to outperform the direct MLE approach.
Wow, so they systematically debunked these different explanations. What did they find out? What's the real reason behind the success of these indirect approaches?
After ruling out all these common explanations, the researchers stumbled upon a fascinating concept. They call it the generation verification gap.
A generation verification gap. Okay, now I've got my attention. Tell me more.
Imagine trying to solve a really complex Sudoku puzzle. It can take a lot of brain power and effort to come up with the right solution. But once you have a solution, it's much easier to verify if it's correct.
Ah, I see. It's like the difference between composing a piece of music and simply listening to it and deciding if you like it. Creating is hard, judging is easier.
Exactly. And the authors suggest that this gap between generation and verification also applies to large language models. Creating a brilliant, nuanced summary is likely much more difficult for the model than simply judging which of two summaries is better.
So are you saying that this two-stage process with the reward model and reinforcement learning somehow taps into this generation verification gap?
That's precisely what they propose. In the first stage, you train the reward model on a relatively simple task, evaluating different outputs like scoring summaries based on how well they meet certain criteria. This reward model essentially becomes a highly skilled judge.
Okay, so the reward model is the expert critic, the one with the refined taste. Then what?
Then reinforcement learning comes into play. It optimizes the policy, which you can think of as the model's overall strategy for completing the task. But here's the key. The policy is optimized within the constraints set by the reward model.
So it's like the reward model is a demanding teacher saying, I'll only accept A-grade work. And the policy or the AI strategy has to figure out how to achieve those top marks within the boundaries set by the teacher.
That's a great way to visualize it. The authors believe that this shortcut, focusing the policy's efforts based on the simpler verification task performed by the reward model, is a major reason why these indirect approaches often outperform direct methods like MLE, especially when the gap between generation and verification is large.
Okay, I'm starting to get the picture. But is there any concrete evidence to back up this theory? I mean, it's a compelling idea, but did they actually prove it?
They did. And that's what we'll dive into next.
Right.
So to test their theory about this generation verification gap, the authors ran a series of really clever experiments. In one experiment, they intentionally simplified the generation task. Instead of having the model create full-length summaries, they had it generate summaries that were only 2 words long.
2-word summaries. That seems incredibly restrictive. What was the point of that?
Well, by simplifying the generation task, they essentially closed the generation verification gap. Remember, the idea is that generation is harder than verification. If you make generation ridiculously easy, then the gap should shrink or even disappear altogether.
Ah, that makes sense. So what happened?
Exactly as they predicted when the generation task was simplified, the performance difference between the online and offline methods vanished. Both approaches performed equally well.
So when the playing field was leveled, so to speak, the advantage of the indirect approach disappeared. That's pretty strong evidence in favor of their hypothesis. Did they run any other experiments to test this?
Yeah, they did. In another experiment, they went in the opposite direction. Instead of simplifying generation, they made the verification task more complex. They used a metric called ρ(L) to evaluate the summaries.
You mentioned ρ(L) earlier. Can you remind me what that is again?
Sure. So essentially, ρ(L) is a way of measuring how well a generated summary matches a human-written reference summary. It looks at how many words overlap between the two summaries, taking into account the order of the words. You can think of it as a kind of plagiarism checker for summaries, making sure the AI isn't just copying the human-written version.
Okay, so by using ρ(L), they made the verification task more nuanced and challenging, and this closed the performance gap as well.
It did, and that's consistent with their theory. If verification becomes more complex, then the generation verification gap shrinks. The two tasks become more similar in difficulty, and the advantage of the indirect two-stage approach diminishes.
So whether they simplified generation or made verification more complex, the results pointed to the same conclusion. This gap between generating something and verifying it plays a crucial role in determining which training methods work best.
Precisely. And they made another fascinating observation. Even when they reduced the amount of data used for training, the online indirect methods still consistently outperformed the offline direct methods.
So even with less information to work with, the indirect approach was more efficient. That's really surprising. I would have assumed that more data would always lead to better performance.
Yeah, it's a common assumption. But this research suggests that it's not always the case. It seems that the efficiency of the online indirect method isn't just about the quantity of data, It's about how that data is used. It's like the difference between passively reading a textbook and actively engaging in a conversation with a knowledgeable tutor. Even if the textbook contains more information, the interactive learning experience with a tutor might lead to deeper understanding and faster progress.
I love that analogy. It makes me think about all the times I've tried to learn something new by just cramming information from a book. It rarely works as well as when I'm actively testing myself, getting feedback, and refining my understanding through interaction.
Absolutely. And that's essentially what these online fine-tuning methods are doing. They're creating a more interactive learning environment for the AI, where it's not just passively absorbing data, but engaging in a kind of dialogue with the reward model to refine its approach and improve its performance.
This research is really changing my perspective on AI training. It's not just about giving the model more data. It's about understanding how it learns best and creating the right conditions for it to thrive.
It's about being more than just data providers. We're becoming architects of learning environments for these AIs.
I like that, architects of learning environments. This whole idea of a generation verification gap has me thinking about those CAP-TCHA tests we see online. You know, the ones where you have to identify traffic lights or crosswalks to prove you're not a robot.
Interesting connection. What are you thinking?
Well, it seems like those CAP-TCHAs are exploiting this same gap. It's pretty easy for us humans to verify those images, but it's much harder for AI to generate them from scratch. It's like we're using our human advantage in verification as a way to keep the robots at bay.
That's a great observation. It highlights how this gap isn't just a theoretical concept. It has real-world applications, even in the way we design security systems.
It makes me wonder if this gap will always exist, or if AI will eventually catch up and be able to generate things just as easily as it can verify them.
That's a question that researchers are actively grappling with. It's possible that as AI becomes more sophisticated, the gap might narrow. But for now, at least, it seems to be a fundamental aspect of both human and artificial intelligence.
It's fascinating to think about this dance between generation and verification. It seems like this constant interplay between creating and judging is at the very heart of how we learn and evolve, both as humans and as machines.
I completely agree. And it's a reminder that even as we develop increasingly complex and powerful AI systems, there's still so much we don't understand about the nature of intelligence itself.
This whole deep dive has been so thought-provoking. It's like we've uncovered a hidden layer of complexity in the way we think about AI training. I'm really starting to appreciate the power of these indirect methods and the importance of understanding this generation verification gap.
And remember, this deep dive has just scratched the surface. There's a whole universe of research and exploration ahead in this area.
This whole conversation has me thinking, what if we could apply some of these AI training insights to our own learning as humans?
Oh, that's a really intriguing thought. What do you have in mind?
Well, we've seen how these indirect approaches with reward models and reinforcement learning can be so effective for AI. Could we as humans create our own versions of reward models to help us learn more efficiently?
It's a fascinating idea. Imagine if we could identify our own personal generation verification gaps. You know, those areas where we're great at judging or evaluating, but we struggle to create or produce.
Exactly. Like, I'm pretty good at telling if a song is well written, but ask me to compose a melody and I'm lost.
Yeah, that's a perfect example. And maybe by recognizing those gaps, we could design learning experiences that specifically target them. We could seek out mentors who excel in those areas, create structured feedback systems, or even design environments that encourage us to practice and refine those skills.
It's like building a personalized curriculum for our own brains, tailored to our unique strengths and weaknesses. We could leverage our natural abilities and verification to boost our skills in generation, almost like hacking our own learning process.
I love the way you think. And it highlights a really exciting possibility. Maybe this research isn't just about improving AI, but about improving human intelligence as well. It could lead to a deeper understanding of how we learn and how to optimize that process.
Yeah, it's a reminder that the pursuit of better AI isn't just about building smarter machines. It's about understanding the nature of intelligence itself and using that knowledge to empower both humans and AI to reach their full potential.
Well said. And I think that's a powerful message to leave our listeners with.
So as always, we encourage you to dive deeper into this research and explore how its findings might apply to your own life and your own journey of learning and growth. Who knows what amazing discoveries await?
Keep asking questions, keep experimenting, and keep diving deep into the fascinating world of intelligence, both human and artificial.
That's a wrap for the deep dive.